Okay, so 10.5 is about rationalizing denominators. Generally, we never really liked leaving negative numbers in the denominator. We also don't like leaving the square roots in the denominator that aren't simplified, because it makes it, we're dividing something into pieces and we're dividing them into irrational sized pieces. It kind of makes it harder to give context for what's actually happening, but it's just a little bit cleaner looking in the numerator. So when we have something like 12 over the square root of 8, of course we can simplify the square root of 8 to 2 square roots of 2. 12 divided by 2 is 6, so this is 6 over the square root of 2. Now, if you've got a square root in the denominator, you can multiply by that square root in the denominator and the numerator of your fraction to help clear it up. That's only if it's by itself. So 6 times square root of 2 is just 6 square roots of 2. Square root of 2 times square root of 2, you can either look at this as the square root of 4, but the square root of 4 is just 2. Dividing here, 6 divided by 2 is 3 square roots of 2. So oftentimes it can clean up pretty nicely. Square root of 27 over the square root of 5. If the whole thing's under the square root, you can apply the square roots separately. Square root of 27 is 3 square roots of 3 over square root of 5, because this is 9 times 3. Again, to clean up the denominator, we multiply by the square root of 5 over the square root of 5. 2 square roots multiplied together, you just multiply them together under the single square root. So this is 3 square roots of 15 all over 5. Square root of 5/8 times square root of 1/6. We can look at this a few different ways. This is the square root of 5 over 2 square roots of 2 times 1 over the square root of 6. When we multiply them together, we get the square root of 5 over 2 square roots of 12. Now the square root of 12 is 2 times the square root of 3, so this is really the square root of 5 over 4 square roots of 3. Even though there's a constant in my denominator here, the only thing I need to multiply by is the square root. I don't mind the constant. So multiply by the square root of 3. This gives me the square root of 15 over, this becomes 3. That's 4 times 3, which is the square root of 15 over 12. The same thing can be done with variables. It's not just numbers. Square root of 4x over square root of y. Well, the square root of 4 is 2, so this is 2 square roots of x over the square root of y. When dealing with the square roots, you can look at the coefficients separately. The square root of the coefficient times the square root of the variable. Now again, to get rid of the square root of y in the denominator, I need to multiply by the square root of y, which means in the numerator as well. So this is 2 square roots of x times y all over y. You might think that that doesn't look more simplified than it started, but it still gets our denominator more simplified when we're dividing in theory. Square root of 2x squared y over 3. Again, this is the square root of 2x squared y over the square root of 3. X squared is a perfect square. It's x times x, so when x comes out of our square root, x squared is a 2y over the square root of 3. The only thing I really need to do to clean up the denominator is multiply by the square root of 3. So this is x times the square root of 6y all over 3. Okay, if you've got a cube root, you really need to look at how much of the factor you're missing. For example, the cube root of 4x squared, 4 is 2 times 2, x squared is x times x. So I have 2 of 2 different factors, but I need 3 to get out of a cube root. You always multiply by the same kind of root, but you need to figure out what's missing. I am missing 1, 2 to get a perfect pair, and 1x, again there. So it's times the cube root of 2x over the cube root of 2x. And when I multiply these, this is the cube root of 4x. Let's look at the denominator now. If I just want to multiply them under the cube root of 4x squared, so 4x squared times 2x is 8x cubed. These are both perfect cubes. The cube root of 8 is 2. The cube root of x cubed is x. This is the cube root of 4x all over 2x. Now, when the terms aren't by themselves, it gets a little more complicated. To see that, I just want to focus on something. Let's say properties of square roots, the square root of 13 minus the square root of 7 squared. So the square root of 13 minus the square root of 7 times the square root of 13 minus the square root of 7. When you FOIL or use the distributive property, square root of 13 times square root of 13 is 13. Square root of 13 minus times the square root of negative 7, where there's a negative square root of 7. It's the negative square root of 13 times 7, which is 91. We've got another one of those. And then the negative square root of 7 times negative square root of 7 is positive 7. Now notice, 13 plus 7 is 20. So this is 20. We have two of the same thing, so 20 minus 2 square roots of 91, which doesn't actually break down further. So you see the problem with square, when there's multiple things under the root and you square it, there's still a root in your answer. However, when you have conjugates, the square root of 17 plus 3 times the square root of 17 minus 3, we have square root of 17 times square root of 17 is 17. Square root of 17 times negative 3 is minus 3 square roots of 17. 3 plus times the square root of 17 is plus 3 square roots of 17. 3 times negative 3 is negative 9. Look what you have in the middle when you multiply by conjugates. We have two things that when I add them together cancel out. 17 minus 9 is 8. So we were able to successfully turn a term with a number and a square root into just a whole number by multiplying by the same exact thing with a negative in the middle. That's important when we move on to this next set. I'm going to skip 3. You can do it yourself. For simplifying rational denominators when there's more than one term down there, using conjugates. So to rationalize denominators, we just multiplied by a single term. That will not work when we have a number and a radical in the denominator, so we need to use that conjugate idea. So the idea here is if I want to kill my middle terms, get both of my terms to the square, I need to take whatever's there and multiply by the same thing with the opposite sign in the middle to get it to work. So if we have 3 plus square root of 5, I need to multiply by 3 minus the square root of 5 to rationalize my denominator. Anything I do to the denominator, I also have to do to the numerator. Now if I distribute in the numerator, 5 times 3 is 15. 5 times negative square roots of 5 is minus 5 square roots of 5. In the denominator, 3 times 3 is 9. 3 times negative square root of 5 is minus 3 square roots of 5. Square root of 5 times 3 is plus 3 square roots of 5. Positive square root of 5 times negative square root of 5 is negative square root of 5 squared, which is just negative 5. Now again, middle terms cancel. So 9 minus 5 is 4. So this is 15 minus 5 square roots of 5 all over 4. And this is simplified with a rational denominator. Same thing happens with variables. I have a square root of x minus 5 in the denominator. I'm going to multiply by the square root of x plus 5. Okay, when I distribute, we have 6 square roots of x plus 30 plus square root of x times square root of x is x plus 5 square roots of x. In the denominator, square root of x times square root of x is x plus 5 square roots of x minus 5 square roots of x minus 25. So let's combine everything we can. In the numerator, I've got x plus 11 square roots of x by combining plus 30 over in the denominator, again, these two cancel over x minus 25. Now, resist the urge to cancel things out. You can't cancel them out when things are added or subtracted, so you're just done here. So your answer is the x plus 11 square roots of x plus 30 over x minus 25. And that is all for section 10.5.